Here we go, kids. I actually made it halfway through this, and I had to answer a phone call that I had to answer. So I'm going to do it again now. We're going to work on this thing called percent composition by mass and the mole problems together. We're going to put it all together and make it beautiful. So you find a bar of pure gold, 324.8 grams exactly. 4 significant figures. How many atoms is that? You can know this, right? You can start by going to the map. Take the map out. You got to have it. You put it on the bottom of table H. That's where you should draw it, on one side. So you have this. This is going to be a two-step math problem. We're going to go from mass island, grams. We're going to switch to moles. That's the only place we can go. There, or we go into the ocean, into the beast. We don't want to get eaten by a shark. To go from mass to moles, you have to know the conversion factor. The conversion factor is 1 mole is equal to the molar mass. Now, this stuff is gold on the periodic table, element number 79. So take out your periodic table and put your finger right in there. The starting point, ba-boom. 324.8 grams of gold over 1. We put it over 1 to remind you that the units, grams of gold, are in the numerator. So when we put in the conversion factor, we put the grams in the denominator so they cancel nice. Now, the molar mass of gold. Put your finger in the box. We round to the nearest whole number. We don't use all those decimals, right? We don't use some of the decimals. Round to the nearest whole number. We're not making medicine for my heart. It doesn't have to be perfect. We have to show that we know the idea of what we're doing. So we agree to always use the nearest whole number. Gold is 197 grams per mole. Now look, we put the grams in the denominator because we have grams in the numerator already, and look what happens, ba-boom, cut them right out, cancel them. And now we put the equal sign because we have the unit we want. We're going to go from grams to moles. There they are, moles of gold. Do the math. Get your calculator. Don't just copy this. Make sure your calculator gives you the same number. Now, there's 4 significant figures. There's 4 significant figures where we started, and in the molar mass, it's unlimited. So it doesn't limit our answer. Our answer is limited to 4 significant figures. Hint on the bottom. Step 2, we're going to convert from moles all the way to atoms. One more big step. You have to rewrite this moles on the left so you have some room. Look what I did. I moved it over there. See with the green arrow? Look what I did. Same thing over there. We put it over 1 because we have to remind ourselves that the moles are in the numerator. Now, the total, or the conversion factor, to go from moles to particles, in this case they're atoms. The particles are atoms. 1 mole equals Avogadro's number, 6.02 times 10 to the 23rd atoms. Now, we got moles in the numerator. We got to put moles in the denominator in the conversion factor. See where they are? Why? Here it comes. Ready? Ka-chink. I cut them right out. Moles are gone. They cancel each other out. And I put another equal sign here because we have the units we want. The answer is going to pop out now. How do you do this math? 1.649 times 6.02 equals. Do the front part first. Then, whatever you get, times 10 to the 23rd. You can't forget all those bazillions. That's a lot of zeros. You can't forget them, right? So we have 4 significant figures times the unlimited in the conversion factor. We're going to have 4 significant figures times 10 to the 23rd. That shouldn't be an equal atoms, okay, right? Well, I guess, I don't know how you wrote it. 9.927 times 10 to the 23rd atoms of gold. I'm going to fix that right now. That bothers me. That little equal sign doesn't belong there. There we go. It's a beautiful thing. Save current slide. Sorry about that. 9.927 times 10 to the 23rd atoms of gold. It's easy. The math is easy. How to do the math? You got to find the map. You got to follow the steps. Otherwise, you go a little crazy. Here we go. 64.35 grams of sodium hydroxide. The compound is ionic because sodium's a metal. Hydroxide's on table E. If you had a small handful of this, like a meatball, 64.35 grams of sodium hydroxide. How many of those grams, how many of the 64.35 are only oxygen? This is also very easy. How do you do it? That's kind of hard. First, in blue, I can't answer. The phones are ringing off the hook. I hung up on them. We need the molar mass. Do the molar mass, okay? I'm waiting for you. Do it. You got plenty of room. Do it on the left side only. Left side, molar mass. The formula, sodium is a +1, hydroxide's a -1, it goes together in a 1-to-1. Look at this, NaOH. 1 sodium, 1 oxygen, 1 hydrogen, 3 atoms in this whole compound. 23 grams for sodium, 16 grams for oxygen, 1 gram for hydrogen, 40 grams per mole. Now, on the right side, we're going to do the percent composition by mass for sodium, for oxygen, and hydrogen. And we want to do all 3 parts to make sure that when we add it up, it gets to 100%. You don't want to do just the oxygen. The question's only about oxygen. But if you do just oxygen, I'm stalling now. Are you doing the work? Stop listening to me. Do the work. If you do it for just oxygen, you make a dopey mistake. You won't know it. You just think, here it is. Do it all. Check your work. It's going to take you like 25 extra seconds, and you've got 25 seconds to waste, right? I promise you, you've got time. Do it right. If you're going to do it this much, you might as well get the whole thing right. So here's the percent comp by mass. The sodium is 23 grams out of 40 grams times 100%. And the oxygen is 16 grams out of 40 grams times 100%. Look how big and bold it is, because that's the one we need. We need the oxygen. And then the hydrogen, 1 gram out of 40. And if you add that up, what do we got? 50, 97, 100%. Works every time. Now, how do we get the answer? We needed to do molar mass so that we could do percent comp by mass, but the question is not about either of those things. This is like setup. This is like practice. This is like warm up. Now, going back to the question, you have a little meatball of this sodium hydroxide stuff. Out of the 64-something grams, how many are just oxygen? 40% of them. How do we figure out 40% of this? This is how. You write the mass that you have times 40%, but you write it like a decimal. 64.35 grams times 0.40 equals the answer. We started with 4 significant figures. All the molar mass and all the percent comp, that's all unlimited significant figures. You could round it to 40. It actually comes out to 40, but you can have as many decimal places as you like. But this is the answer. 4 significant figures in the answer. Not hard. Molar mass, easy. Percent comp by mass, very easy. Even this bottom part in green, it's not hard. But from the question, did you know 1 step, 2 step, 3 step? That's the tricky part, right? It's like a dance. Anybody can move their foot to the left. You got to do it in the right order. Otherwise, you look a little funny out there like me. I don't dance too well. I'm good at this. I'm not a good dancer. It's easy, though. Easy to dance. It's easy to do this. Here we go. Look at this beautiful digital image of a gigantic balloon. This is a big balloon, 346 liters. That's my box, the wooden box I showed you, that's 22.4. This is freaking gigantic. How much does it weigh? What's the mass of the balloon if the balloon is filled up with just neon gas? What's the mass? So we know the volume, and we want to know how much is the mass. So we're going to start at the island on the top. See where my hand is on the top? We're going to switch to moles, and then we're going to switch over here into grams. 2 steps. This is the biggest problem in the world. What is that in the top left corner? Assume STP. What is STP? Special toothpaste. No, that's not it. Silly teacher person. That might be it too. STP, standard temperature and pressure. Now, in our class, all of our gases will always be at STP, standard temperature and pressure, because at STP, 1 mole is 22.4 liters. Later, when we get to gas chemistry, we'll change the pressure a lot. We have all different kinds of units too, and we'll change the temperature a lot, and we change them both. That changes a lot of things, but when you're at STP, standard normal temperature, standard normal pressure, 22.4 liters is exactly 1 mole. We're gonna, all our gases now, STP. So volume to moles. So we're gonna start, where do we start? Look, 346 liters over 1. That's the starting point. To get from volume to moles, we need to remember the total, or the conversion factor. 1 mole equals 22.4 liters. Write your units. Look, we got liters in the numerator. We got to put the liters in the denominator. Look at this. Because watch what happens. I love this when I do this with my other hand. Look. Cancel out those liters, and we switch liters into moles. If I say I have 346 liters of neon, You could say, hey, I got 15.4 moles in neon. We got the same thing. They're equal to each other. It's just a conversion. We converted it from liters into moles. Look at the hint on the bottom. Convert moles into grams. Okay, let's move this 15.4 liters over so we have some room to work. Now, to go from moles to mass, we have to remember the total. We need to know that 1 mole equals the molar mass. What the heck is the molar mass for neon? Take out your periodic table. I'm going to wait. Neon happens to be element number 10 on the right-hand side underneath helium. Stick your finger in a box, and we round this number to the nearest whole number. We don't use decimals. No decimals for molar mass. Round it to the nearest whole number. 1 mole. See how we have moles in the numerator? We put the moles on the bottom. 1 mole is 20 grams for neon. Look at that. 20 grams of neon over 1 mole of neon, that equals 1. It's a conversion factor. What? Here it comes. Ready? Goodbye, moles. And since we got grams there, time for an equal sign. Somebody just rang my bell. I'm having the hardest time. Take a quick break. Oh, really? Yes. Well, thank you so much. Are you 61? I can see. You're the last. I'm the baby. Well, I'm sorry. I love you, baby. I mean, that's right. I usually do. Thank you so much. Thank you. Okay, kids, I'm sorry it took a moment. It was my neighbor, my New Yorker magazine, which I love. Apparently, he got it in the mail. He gave me a birthday card and a little present. I think he gave me some apple juice. I love apple juice. All right, 308 grams. I'm really sorry that I delayed it. This is so hard because I'm a person and there's people keep jumping into my life. And I already did half of this. I already went past this and had to start over. So here we go. This part of chemistry, honestly, is stupid. I say in bright red, and it is. I understand empirical formulas. I see no need for them at our level of chemistry. They're confusing. They're stupid. So here's the deal. There are things in chemistry that are complicated. This is not complicated, but it's confusing, and there's no reason for it. I wish I didn't have to teach it to you, but it's worth a point on the regions. It's a good word, empirical. Here we go. When you were in high school biology last year, which you probably passed because now you're in chemistry, you learned about glucose. Glucose, C6H12O6. Let's talk about this formula. The ratio of carbon to hydrogen to oxygen is 6 to 12 to 6. And there's nothing wrong with that. You know that stuff. You eat your food and it turns to glucose. The sugars break down into simple sugars like glucose. Glucose is what they give you in an IV when you're in the hospital. It's good stuff. But it breaks the rule. John Dalton, I've been telling you, simple whole number ratios, right? You can't have 2 to 4. You got to make it 1 to 2, right? What Dalton didn't know was that there are organic molecules, especially the ones that obviously have carbon in them. Carbon does weird things that he didn't know about. Carbon doesn't just bond to oxygen or doesn't just bond to simple hydrogens. It can make chains. It can make big molecules, rings and chains and rings or chains and branches. It does all kinds of stuff. So the simple whole number ratios do not hold true for organic molecules. The larger organic molecules break that simple rule. We'll learn about organic chem later in the year. It's not hard, but we can't teach you everything at the beginning, and every once in a while I got to kind of say, well, there's a little exception we got to learn about. This is a stupid exception, but there are molecules like this that do not follow that simple rule, and that's because he didn't know about them. It's a great idea, simple whole number ratios, and it works for most chemistry, but there are larger organic molecules that don't do that. Now, 6 to 12 to 6, what does that mean? That means reduce 1 to 2 to 1. 6 to 12 to 6, if you divide them all by 6, becomes a 1 to 2 to 1 ratio. Now, if I were to say All right, let's look at this big molecule formula. What's the ratio of carbon to hydrogen to oxygen? I don't know why I would say that. I could say that, and you're smart enough to figure it out. 6 to 12 to 6 is reduced to 1 to 2 to 1. And I guess we could talk about that. I don't know what we would talk about. There we go. We talked about it. I don't know why you would want to know this, but it's easy. The problem is an empirical formula is not just about the ratio. They want you to write it so that the ratio looks like a formula. So let's look at this next slide. Glucose on the top in black, the empirical formula in a 1 to 2 to 1 ratio is CH2O, carbon 1, hydrogen 2, oxygen 1. You have to write it like a formula. Now, here's the deal. Most empirical formulas don't even work. They can't exist. As it turns out, this could exist. You could get these 4 atoms to bond together into a molecule, but it's not a sugar, it's not sweet, it's certainly not glucose, and we're not going to talk about it for months and months and months. This is weird. Why do you have to learn this? Because New York State says you got to learn it. It's easy, but it's annoyingly confusing. Let's see if we can do a few of these. Empirical formulas in math. Most empirical formulas can't even bond together, and even if they do, they're certainly not the same compound. They just share a ratio. CH2O does not exist. It looks like chemistry, but it's math. Let's do some. They're really easy. For example, you don't have to know any of these names. I just give you names so that you can know that they're really not just made up. C6H14 is something called hexane. The ratio of carbon to hydrogen is 6 to 14. Both of those numbers are even. They can both be divided by 2. 6 to 14 can be reduced to 3 to 7. And instead of just saying the carbon's in a 3 to 7 ratio with hydrogen, the empirical formula says write it like a formula. Now this stuff, C3H7, those 10 atoms cannot bond together. That will not work. It never can work, but it's an empirical formula. Are you good with that? Put it in your pocket. I don't know what you're going to do with it. You carry it around all day, has no value. This next stuff you put in a car. This is gasoline. Gasoline is real name octane. Oct is for 8 carbons. C8H18. What's the ratio of carbon to hydrogen? Look, it's 8 to 18. They're both even numbers. Divide them by 2. That means it's the same as a 4 to 9 ratio. So the empirical formula is C4H9. Put that in your other pocket because it has no value. That's how you write the empirical formula. I cannot believe how many people want to talk to me. I'm hanging up on them too. Next one's candle wax. You having a birthday? I just had a birthday. I blew out some candles. They put them in a bagel. My daughter brought me cinnamon raisin bagels, handmade into the number 60. So I had these 2 big bagels in the shape of a 60 because I turned 59. No, I turned 60. C24H48. Now, this is tricky business. You can divide it by 2 and you keep dividing it till you get the ratio. This one's going to ratio out to 1 to 2. So to write the empirical formula, it's CH2, 1 carbon, 2 hydrogens. Now look at this thing. It's got, what, 72 atoms, but the empirical formula's got 3. And CH2 can't bond together either. So we got 3 empirical formulas that don't even exist. They're just math. Acetylene. I once used acetylene. I welded 2 pieces of metal together. A friend of mine's brother is a welder. I always wanted to try it. Oh my gosh. I'm not answering that either. Acetylene's in a 2 to 2. That rounds to 1 to 1. CH. That's the empirical formula. Also can't exist. It's not a compound. Hydrogen peroxide. H2O2. Weird formula. We'll get to that. This is kind of an odd ionic thing. We'll get to it another day. 2 to 2 becomes 1 to 1. HO. That's the empirical formula. It's not a real formula. HO can't exist as a molecule. Cyclohexene. Now, there's a fun thing to say. Hey, there's the cyclohexene. That's really, actually, it's cancer causing. You don't want it near you. 6 to 6. That reduces to 1 to 1. Look, it's got the exact same empirical formula as acetylene. Acetylene is good. I mean, you can't breathe in it. It's very flammable. Cyclohexene gives you cancer. It has the same empirical formula. Is that valuable information? It's worth the point on the regions. Decane, 10 carbons, C10H22. They're both even. 10 and 22 are both even. You could divide them by 2. And what do you get? 5 to 11. So you're right, C5H11. That can't bond together either. We haven't gotten lucky yet. None of this stuff works. The empirical formulas are just mathematical constructs of the reduced ratio. They're not real. Pentene. Now this isn't pentene. 5 carbons, but not pentane. Anes are different than enes, and we'll get to that another day. 5 to 10. 5 to 10 reduces to 1 to 2. Look, this has the same exact empirical formula as candle wax. It's not candle wax. These two things happen to have the same empirical formula. It's kind of like if anybody in the class has a size 10 and a half extra wide sneaker. That doesn't make us twins. It means we wear the same sneaker. I don't know what it means. It means you got big feet like me. CH2 doesn't exist, cannot bond together, it doesn't work, but that's the empirical formula. It's in a 1 to 2 ratio. Here's pentose. Pentose sounds like glucose. Anything that ends in OSE is a sugar. This is a sugar that you don't eat too much. Pentose is in a 5 to 10 to 5. That can be reduced to 1 to 2 to 1. Look, it's got the same empirical formula as glucose. It's not glucose. It doesn't taste like glucose. It doesn't have the same properties as glucose. It has the same, like probably wears a size 10 and a half wide sneaker like me and you, one of you. Empirical formulas are not hard. I don't know what their value is, literally, except they're worth 1 point on the Regents. Okay. It actually gets a little stupider. But this is still, believe it or not, this is not the stupidest thing in chemistry, but you have to learn a couple of stupid things. But this is only like the 3rd stupidest. I don't know who this matters to, but here we go. Let's look at these formulas. You know what water is? H2O. H2O is in a 2 to 1 ratio and cannot be reduced. So the formula for water is H2O. And it also has an empirical formula, which is H2O. What are you going to do with that information? Methane is CH4. That's the molecular formula. You need 1 carbon and 4 hydrogens, and that bonds together. That's a molecule. But 1 to 4 can't be reduced, so the empirical formula for methane is CH4 also. This is kind of like, my name is Charlie Abuso, and if you can't remember that, call me Charlie Abuso. What else could you call me? Carbon dioxide, CO2. 1 to 2 cannot be reduced. So what's the empirical formula? CO2. Empirical formulas are not too tough. All right, where are we? One last problem, and we're going to be done with this. Really? Oh, I think we're done. Yeah, we got one last problem. Sorry about that. You find 131.25 moles of silver, 5 significant figures. Silver's selling for $24.22 a gram. I just found that out the other day. Put the star on. That was from like a couple of days ago. That's legitimately pretty current. Are you rich or happy? Did you make a lot of money? How many grams? You got this many moles. How many grams is that? We got to do some math. We're going to go from moles to grams. And then we're going to multiply the grams by how much of this money per gram and see if you make a lot of money. So let's go from moles of silver to grams. One-step conversion. From moles to grams, you need the molar mass of silver. Put your finger in box 47. Box 47 is silver. And silver has a molar mass that rounds to the nearest whole number called 108 grams per mole. The moles in the numerator cancel the moles in the denominator. Here it comes. Ready? Ka-chunk. I got rid of them. And the answer is going to come out in grams. Multiply across the top. It's going to be a lot of grams. It's not a bad day. All right. So 14,175 grams. Kind of a lot of grams. Now, silver is only $24 and change a gram. Goes up and down a couple of pennies every day, unless something crazy happens. But I think it's pretty close. Now we multiply those grams times the price of silver. We get rid of the grams and convert it to dollars. Watch how this happens. The number of grams over 1, and that conversion factor on the bottom, look, it's $24.22 per gram, and the grams cancel. So if you happen to find 131.25 moles of silver, more or less, not too shabby. It's a lot of money. That's the back of a silver dollar, silver half dollar, 50-cent piece. I don't see them too much. You certainly don't see them so shiny if you do. Chemistry's great. Math is math. Try to make the best of this. try to do the notes, try to use the map, always use your units. Peace, love, and chemistry. Bye-bye.